Today I want to discuss the wind energy as a renewable energy sources in this lecture. The today's content is the what is wind, how the wind occurs globally, the parameters of wind speed variations, what is the turbulence, the mathematical expression governing the wind power, the major components of a typical wind energy conversion system, and the operation of a typical wind energy conversion system. Now, what is wind? The wind results from expansion and convection of air as solar radiation is absorbed on Earth. The wind is a byproduct of solar energy. Approximately 2% of the sun's energy reaching the Earth is converted into the wind energy. The surface of the Earth heats and cools unevenly, creating the atmospheric pressure zones that make the air flow from high to low pressure areas. The wind has played an important role in the history of human civilization. The first known use of wind dates back 5,000 years to Egypt, where the boats used sails to travel from shore to shore. The first true windmill, a machine with vanes attached to an axis to produce the circular motion, may have been built as early as 2000 BC in the ancient Babylon. Now, on a global scale, these thermal effects combine with the dynamic effects from the Earth's rotation to produce the prevailing wind patterns. The kinetic energy stored in the winds is about 0.7 into 10 to the power 21 joules, and this is dissipated by friction, mainly in the air but also by contact with the ground and the sea. In general, the wind speeds increase with height, with the horizontal components significantly greater than the vertical components. Wind speed varies significantly with time over periods from seconds to seasons and years, and over the distances approximately 1 kilometer, especially in the hilly terrain. Therefore, it is important to make the measurements at the nominated site at several heights for at least 12 months and compare these with the official meteorological data and the wind atlas information. Now, how the winds occurs globally. Air is transparent to solar radiation and so is not heated until the radiation is absorbed in the ground and the ground heats the air above. The heated air near the ground expands, becomes the less dense and rises through the colder air above. The heating effect is strongest near the equator. This is the equator shown in the figure. This causes the looped convection currents in the lower atmosphere at the troposphere to the height of 15 km. The thickness of the atmosphere is exaggerated by the factor of 100, which is shown in the figure. This is the loop. This is the air, warm air. This is the cold air. This is the North Pole at the northerly surface winds. This is the southerly surface winds. This is the South Pole, and this is the equator. So figure portrays this scenario, producing a pair of sails of circulating air as the first depicted by Hadley in the 17th century. Now, in the real life, this single sail circulation cannot be sustained over the long distances, approximately 9,000 km between the equator and the poles, within a relatively shallow atmosphere, approximately 15 km. The circulation breaks up into the three sails in each hemisphere as shown in the 11.1b. Rising air at the equator descends around latitude 30 degree, continues towards the pole near the surface until about the latitude 60 degree, then rises before the continuing towards the pole in the upper atmosphere. This is called the polar sail, this is called the Ferrel sail, and this is called the Hadley sails. Okay, so these three sails are there in each hemisphere. Now in tropical regions, a parcel of air near the surface of the earth is pushed towards the equator by the thermal circulation, thus moving to a region where the rotational speed of the earth is greater than that where the air came from. So the parcel of air is left behind by the surface underneath and arrives at a point to the west of where it would have been. It is moved purely from the north to south. Purely from the north to south. This is the loop. Thus the wind appears to an observer on the surface of the earth to be coming from the northeast in the northern hemisphere, and this is the northeast at the northern hemisphere, and from the southeast in the southern hemisphere. This usually moderate the prevailing any or AC wind is called the trade wind. This is called the trade wind. Okay, so owing to the use sailing the ships made of it. Northeast and southeast wind. Northeast and southeast wind is called the trade winds. Similarly, the polar sail sets up strong polar easterly winds, which are shown in this figure. In the mid latitudes where the surface air is going towards the poles, it is moving into the regions of slower rotational speeds and is therefore traveling faster than the new surfaces. An observer here senses the wind blowing from the west, the so-called westerlies. A westerly wind is one coming from the west. This is the westerlies at the northern hemisphere, and this is the westerlies in the southern hemisphere, and these are the polar easterlies at the northern hemisphere, and this is the polar easterlies in the southern hemisphere. So now the westerly component of this mid latitude wind is stronger than that of the easterly component in the trade winds, because the difference in the rotation speed across the latitude is greater. On Earth, an atmospheric circulation takes place, which is shown in the picture, which is triggered by the temperature difference on the ground at the equator and poles. The sun virtually perpendicular trajectory over the equator produces much more heat in that area. Then the shallow angle the sun trajectory follows the relative to the Earth's pole. During the year, the sun changes its noon time angle from the perpendicular over the northern tropic to perpendicular over the southern tropic. The change in angle leads to the stronger insolation on the northern hemisphere from April to September and stronger insolation on the southern hemisphere from October to March. Thus, the different pressure areas which trigger a large circulation between the equator and the poles are formed. Because of the Earth's rotation, a direct flow between the anticyclone and the depression is prevented. In the northern hemisphere, the air masses are deflected to the right, and in the southern hemisphere to the left. For that reason, three large circulation cells are generated, that is Hadley cell, Ferrel cell and the polar cells, which are shown in the figure. This is the Hadley cells, this is the Ferrel cell and this is the polar cells in this figure. The main effect of the atmospheric circulation is the continuous transport of the humidity from the equator to the north and to the south tropics. Transport of hot air and humidity from the tropics to the temperature zone. Transport of warmer air and the humidity from the temperature to the colder zones. At the equator, the air rises up. This is the rising air at the equator. The air is rising up because of the strong heating by the sun. At the tropopause, that is the temperature inversion in about 18 km above the ground, the air masses will deflect to the north and the south through area correction. The air masses slide down to the poles. Now, what is the Hadley cell? Through the Earth's rotation, the winds fall until the 30th latitude and the flow back to the equator as the trade winds. At the equator, these winds meet in the intertropical convergence zone. This circulation is called the Hadley zone. This is the 30th latitude. At the north, in the south. Now the polar cell near the 60th latitude, that is 60th latitude, and this is the 60th latitude. So near the 60th latitude, the winds are heated and rises up on the way to the south. This circulation is called the polar cell. Now come to the third cell, that is the Ferrel cell. Based on the air ascent, that is the 60th latitude. This is the 60th latitude. And the air cooling the 30th latitude, a third circulation is formed in the area between the 60 degree and the 30 degree latitude. This is the circulation is called the Ferrel cell. During the ascent process, the air cools down, the humidity inside the condensed clouds are built, and it starts to rain very strongly. In the descending processes, the exact opposite is happening. The air warms and the water is in it starts to evaporate. Desert areas such as the Sahara or the Namib Desert around the 30th latitude are consequences of this process. There are several anticyclones in this region which is caused by the warm air on the ground. These are assigned to the subtropical ridge, that is called the horse latitude. Near the ground level, there is an air transport towards the poles, where the air flows towards the equator at the higher levels. In the northern hemisphere, the air on the ground is distracted to the right, and in the southern hemisphere to the left. The winds from the west are called the westerlies. The polar front is located on the border between the polar easterlies and the easterlies, cold and the warm. This border is usually between the 68th and the 78th latitude. In this area, the depressions often occur. Now the parameters of wind speed variation. Number one is the effect of oceans and continents. Extreme winds occur in the hurricanes, that is the tropical cyclones, and the monsoon, as the moisture, mostly taken from the ocean, condenses to water, which with the release of latent heat. Similar effect but less extreme occurs in all cyclonic weather, as air not only circulates but moves upwards and downwards. These movements are experienced as wind. Second effect is the effect of landscape. The complex terrain of the hills and the mountains deflects and concentrates the air movement, with the significant effect on wind. Daily variation of such winds occurs due to the uneven solar absorption and the height differences, and with the concentration as in valleys. Movement of air over mountains may lead to deposition of air on the windward sides, and the air warmed by its increasing pressure on the leeward side. That is called the foehn wind. Third is the effect by the season and time. In the great majority of locations, average wind speed and direction depends on the season in the year, and in many locations on the time of the day. The meteorological service know these effects well and can make reasonably reliable forecast. However, there is almost complete ignorance about the predicting variation from year to year, which for wind power can cause significant variation, affecting the economics of the installations. Now the next topic is the turbulence. The turbulence is change of wind speed and wind direction in the both the horizontal plane and the vertical direction. When the wind passes over the land, the unevenness of the ground and the interference to the wind flow from trees or the undergrowth will cause a significant amount of turbulence. Meteorologists speak of the planetary boundary layer as the lowest region of the Earth's atmosphere, where there is marked the turbulence caused by the friction with the ground and disturbance by obstructions such as trees, large buildings, cities, and hills. This boundary layer varies in thickness from about 250 meter over the sea to about the 500 meter over the cities and the crest country. Now the mathematical expression governing the wind power. The wind power is generated due to the movement of wind. The energy associated with the with such movement is the kinetic energy, and is given by the following expression as energy is equal to the kinetic energy is equal to half mv square, where the m is the air mass in kg, equal to the volume into density, that is equal to q into rho, where q is the discharge and rho is the air density, and v is the velocity of air mass in meter per second. Hence the expression for power can be derived as follows. The power is equal to d by dt is equal to half of d by dt mv square, that's equal to half of d by dt rho q v square, that's equal to half of rho dq by dt into v square. Here the dq by dt is equal to the rate of discharge, that is meter cube per second, that's equal to a into v, that is meter square into meter per second, where a is the area of the cross section of the blade movement. Blade is the, this is the turbine blade, which I will discuss in later. We know that for the given length of the blades, the power is expressed as power is equal to the half of rho into a into v cube. Here the a is the constant, the area of the blade, and so is the air mass density is equal to the rho. Hence we can say that the wind power is directly proportional to the wind speed cube, that is the v cube. At sea level, rho is equal to 1.2 kg per meter cube. Therefore, the power is equal to half of 1.2 into a into v cube. So the power per area is equal to 0.6 into v cube, that is the power density in watts per meter square. Now come to the major components of a typical wind energy conversion system. The system, a typical wind energy conversion system, is shown in this figure. A wind energy conversion system is an apparatus for converting the kinetic energy available in the wind to mechanical energy that can be used to power machinery, that is called grain mills, water pumps, etc., and or to operate an electrical generator. Thanks to the extensive R&D efforts during the past 30 years, the wind energy conversion has become a reliable and competitive means of electric power generation. The lifespan of the modern wind turbines is now 20 to 25 years, which is comparable to many other conventional power generation technologies. The average availability of commercial wind power plants is now around 98%. The cost of wind power has continued to decline through the technological development, increased the production level, and the use of the larger turbines. Now the major components of a typical wind energy conversion system include a wind turbine, a generator, interconnection apparatus, and the control system. Now first component is the turbine, the wind power plant. The wind power plants produce the electricity by having an array of wind turbines in the same location. The placement of a wind power plant is impacted by the factors such as the wind conditions, the surrounding terrain, access to electric transmission, and other setting considerations. In a utility scale wind plant, each turbine generates the electricity which runs to a substation where it then transfers to the grid where it powers our communities, shown in the figure. The flow of the current from the wind turbine to the through the line to the control system, then it is come to the grid, then from grid to the commercial use applications. The turbine also has a computer built into the detect when to turn on or turn off if the wind speed exceeds a certain mph. Then the machines gets to work. Now the second component is the blade. The most turbines have the 3 blades which are made mostly for the fiberglass turbine blades vary in size, but a typical modern land-based wind turbine has the blades of over 170 feet, that is 52 meters. The largest turbine is the GE's Halite X offshore wind turbine with the blades of 351 feet long, about the same length as a football field. Then when the wind flows across the blade, the air pressure on one side of the blade decreases. The difference in air pressure across the two sides of the blade creates both the lift and drag. The force of the lift is stronger than the drag, and this causes the rotor to spin. This is the rotor to spin. Now the third is the pitch system. The pitch system adjusts the angle of the wind turbine's blades with respect to the wind, controlling the rotor speed. By adjusting the angle of the turbine's blade, the pitch system controls how much energy the blade can extract. The pitch system can also feather the blades, adjusting their angle so they do not produce the force that would cause the rotor to spin. Feathering the blades slows the turbine's rotor to prevent the damage to the machine when the wind speeds are too high for the safe operation. This is the pitch. Okay, so this is the pitch shown in the figure. Now the next component is the rotor. This is the rotor. Okay, so this is the rotor. The blades and the hub together form the turbine's rotor. The next component is the main shaft bearing. This is the main shaft bearing. Okay, the part of the turbine's drivetrain. The main bearing supports the rotating low-speed shaft and reduces the friction between the moving parts so that the forces from the rotor don't damage the shaft. Next is the low-speed shaft. This is the low-speed shaft. This is the low-speed shaft. Okay, so part of the turbine's drivetrain, the low-speed shaft is connected to the rotor and spins between the 8 to 20 rotations per minute. Next is the gearbox. So this is the gearbox. This is the gearbox shown in the figure. The part of the turbine's drivetrain, the gearbox connects the low-speed shaft to the high-speed shaft and increases the rotational speeds from about 8 to 20 rotations per minute to about 1000 to 1800 rpm. This is the rotational speed required by most of the generators to produce the electricity. Now the next component is the very much important component, that is the generator. This is the generator and this is the generator. So the generator is driven by the high-speed shaft. Copper winding turn through a magnetic field in the generator to produce the electricity. Some generators are driven by the gearboxes shown in here. This is the gearbox, and others are direct drives where the rotor attaches directly to the generator. For small to medium power wind turbines, the permanent magnet generators and the squirrel cage induction generators are often used because of their reliability and the cost advantages. The induction generators, the permanent magnet synchronous generators and the wound field synchronous generators are currently used in the various high power wind turbines. Next component is the nacelle. The nacelle sits atop the tower. These are the nacelles. This is 1 and 2. This is the upper and this is the lower. The nacelle sits atop the tower and contains the gearbox, low and high speed shafts, generator and brake. This is actually the cover. Some nacelles are larger than a house, and for a 1.5 megawatt geared turbine can weigh more than 4.5 tons. Next component is the jaw system. These are the jaw system. The jaw drive rotates the nacelle on upwind turbines to keep them facing the wind when the wind direction changes. The jaw motors power the jaw drive to make this happen. The downwind turbines don't require a jaw drive because the wind manually blows the rotor away from it. Now the next component is the anemometer. The anemometer measures the wind speed and transmits the wind speed data to the controller. The interconnection apparatus are devices to achieve the power control, soft start and the interconnection functions. Very open power electronic converters are used as such devices. Most modern turbine inverters are forced commutated PWM inverters to provide a fixed voltage and fixed frequency output with a high power quality. Both the voltage source voltage controlled inverters and the voltage source current control inverters have been applied in the wind turbines. For certain high power wind turbines, the effective power control can be achieved with the double PWM converters, which provide a bidirectional power flow between the turbine generator and the utility grid. It should be noted that the turbine gearboxes are much like the gearboxes of other industrial machines. These require the lubrication, maintenance and open a huge upfront cost. While the petroleum may indeed be used in this turbine component, this is but a small percentage of oil's involvement in the production of alternative wind energy. Now the operation of a typical wind energy conversion system. A wind turbine turns wind energy into the electricity using the aerodynamic force from the rotor blades, which work like an airplane wing, or the helicopter rotate blades. This is the helicopter rotate blades. When the wind flows across the blade, the air pressure on one side of the blade decreases. The difference in air pressure across the two sides of the blade creates both lift and drag. The force of the lift is stronger than the drag, and this causes the rotor to spin as shown in the figure. The wind acts as the force which gets the rotor spinning. The rotor is comprised of the blades and central hub to which they are adhered. As this hub rotates, it turns a low speed shaft, which in turn hooks up to a gearbox. The slow moving gears on the low speed shaft interlock with the fast moving gears on a high speed shaft. converting the 30 to 60 RPMs to about 1000 to 1800 RPMs, the hotspot for the electricity generation. The rotor connects to the generator. This is the generator. Rotor connects to the generator either directly if it's a direct drive turbine or through a shaft. This is the shaft. Through the shaft and a series of gears. These are the gears. Series of gears that speed up the rotation and allow for the physically smaller generator. This is the gearbox. In the gearbox there are several number of gears are there. This translation of aerodynamic force to rotation of a generator creates the electricity. Now these are the references from where I take the materials of this lecture. You will go through these references, then you will get more knowledge on that. Thank you.